These are proving trig identities from page 417. I'm going to show you some of question 10. The first one is cosine times tan cubed. Trying to prove that that equals sine times tan squared. Well, I didn't have a great place to start, but I know tan is sine over cos, which means tan cubed is sine cubed over cos cubed. And then I noticed that a cosine will cancel out with the cosine on the bottom, so I just cross off one cosine and one of these three, leaving cosine squared on the bottom and sine cubed on the top. There wasn't much place else to go there, so I went over to the right hand side, said, well, sine x times tan squared x, that's just tan squared being, just like the cubed here made sine over cos cubed, the squared here makes the tangent being sine over cos also squared because tan was squared. And then I just multiplied top times top, sine times sine squared is sine cubed, and that's what I wanted because now I have sine cubed over cos squared, which is the left hand side. So since the left hand side equals the right hand side, therefore I've proven the identity true. Over to 10b here. For 10b, I wanted to prove that sine squared plus cosine to the power of 4 equals cosine squared plus sine to the power of 4. For me, this is one of the harder ones. It took me a few minutes to solve this one. What I did was say, alright, I'm not sure where to go, but I know that cosine squared is 1 minus sine squared, and so it turns out that it's equally true that cosine to the power of 4 is 1 minus sine to the power of 4, for the exact same reason that cosine squared is 1 minus sine squared, cosine to the power of 4 is 1 minus sine to the power of 4. So leaving the sine squared alone for a bit, I then broke this down into difference of squares. It's like 1 minus x to the power of 4, that's just 1 minus the thing squared, and 1 plus the thing squared. And now I use my rules to simplify. I know that 1 minus sine squared is cos squared, and I couldn't do much with this bracket yet, so I just left it. And then rainbowed this cos squared. So sine squared is just sitting outside here. 1 minus sine squared is cos squared. Now I'm going to rainbow this cos squared in. Cos squared times 1 is just cos squared. Cos squared times sine squared is cos squared sine squared. Why was that helpful? Because now I have sine squared plus cos squared, and from my formula sheet, sine squared plus cos squared is just 1. So I wasn't sure what this meant, but I've sure broken this down a bit to 1 plus cos squared sine squared. Then I thought, okay, let's see if I can do the same thing with the right hand side. Cos squared plus sine to the power of 4. So I went with the same thinking as before. I left the cos squared, the thing in front, but I broke sine to the power of 4 into 1 minus cos to the power of 4. So leaving the cos squared again, I broke that down even further, difference of squares. 1 minus cos to the power of 4 is the same as 1 minus cos squared times 1 plus cos squared. And like before, 1 minus cos squared can be written as the other squared version, this one's sine, so 1 minus cos squared is sine squared. Leaving the 1 plus cos squared alone, on the next line, I rainbow it in. Sine squared times 1 is just sine squared. Sine squared times cos squared is just sine squared cos squared. And once again, I have in front cos squared plus sine squared, which just equals 1. And what's left over, sine times cos, is the same as cos times sine. So sine squared cos squared is the same as cos squared sine squared. And look, left side equal to right side. So I'm good because I've proven it true. That's 10b. For 10c, it was a big one to start. I had sine plus cos times tan squared plus 1 over tan x. And on the right hand side I had 1 over cos plus 1 over sine. I started with the right hand side trying to figure out what to do. First, make it a common denominator. So I want them both to be out of cos and sine. This one's missing a sine, so times top and times the bottom by sine. And this one's missing a cos, so times the top by cos times the bottom by cos. When I have a common denominator now, I can just add the numerators together. I get sine x plus cos x over cos times sine. But I'm pretty much stuck there. So we'll see if I can work that on the left hand side. So leaving the sine x plus cos x for now, and I'm going to want it in the end, so I probably don't need to do anything with that. What I need to do is work with this tan squared plus 1. Well, from my formula sheet, I know that tan squared plus 1 is the same as secant squared. So I have secant squared over tan x. Now I'll use some more conversions. Secant squared is the same as 1 over cos squared, and tan is sine over cos. So I have these two fractions in a fraction. So I'll rewrite that. This is sine x plus cos x times the numerator, 1 over cos squared x. And then when you're dividing by a fraction, it's the same as timesing by its flip. So I flipped cos x over sin x. And what I got was the sin x plus cos x stays, but I can cancel a cos x here with a cos x here. This is cos squared, so there'll be just 1 cos x left on the bottom times sin x, which is perfect because on the top then I have sin x plus cos x times 1, which is just sin x plus cos x. And on the bottom I have cos x times sin x, which is my right-hand side. So once again, since the left-hand side equals the right-hand side, I've proven it true. For question D on page 417, 10D, it's trying to prove that tan squared plus cos squared plus sine squared is equal to 1 over cos squared. There's nothing I can really do with 1 over cos squared, maybe do the 1 minus sine squared, but I just left it because what I recognized right away was cos squared plus sine squared equaled 1. So this whole piece just became 1, and that made my life so much easier. Now what I just needed to do was common denominator. So make this out of cos squared. 1 is the same as cos squared over cos squared. So now just add the numerators together. You get sine squared plus cos squared all over cos squared, and sine squared plus cos squared is 1. So I ended up with 1 over cos squared, which is my right-hand side. So since left-hand side equals right-hand side, therefore proven 10D true. And finally, for this page 10E, I wanted to prove that sine of pi over 4 plus x plus sine of pi over 4 minus x equals root 2 cos x. Well, nothing I can do really with root 2 of cos x. So instead I focused on the left-hand side, and I used my double angle formulas. So take a look at your formula sheet. There's a thing for sine of a plus b, another formula for sine of a minus b. So I just expanded. You get sine of pi over 4 cos x plus cos of pi over 4 sine x, that's for the first one, plus sine of pi over 4 cos x minus cos of pi over 4 sine x for the second one. Those are straight from your formula sheet. Well, then I evaluated using special triangles. Sine of pi over 4 is just 1 over root 2, so you get 1 over root 2 cos x. And then sine of pi over 4 cos x, well, that's just another 1 over root 2. That's sine of pi over 4 times cos x. What happened to these two pieces? Well, take a look closely. This is cos of pi over 4 sine x, and this is minus cos over pi over 4 sine x. This is just one thing, subtract itself. I just canceled them out, which is great because now I'm left with a lot smaller equation. So what can I do with it? Well, what I did here was say, look, this is 1 over root 2 cos x plus another 1 over root 2 cos x. You get 2 over root 2 cos x. And then what I did was I timed the top by root 2 and timed the bottom by root 2. So you get 2 root 2 over root 2 root 2. Well, the root 2 times root 2 gives you 2. And that's good because then on the top and bottom they cancel out. 2 and 2 cancel out, and you're just left with root 2 cos x. I can go through that again really quickly. This is 2 root 2 cos x, but I'm trying to get to root 2 cos x. So I times the top by square root 2 times the bottom by square root 2. When I did that, the denominator, any root times itself, just gives what's inside, 2. And that was good because the bottom 2 canceled out with the top 2, and I was just left with root 2 cos x. Well, once again, the left side equaled the right side, and since that was true, I've proven the original trig identity true.